Ladies and gentlemen, friends of ITU, and also welcome online, the people who are joining us from the outside. Welcome to the first lecture. So we are already in the second part of our series of where we want to introduce our cool new rockstar professors here at ITU. And today, we have the topic of AI-powered science. This is a second focus research area which we want to endeavor and research in the future. So the last lecture was on human-AI collaboration, HCI, human factors. And today we're talking about how can AI revolutionize, inform, further develop science. Different kinds of scientific disciplines, and what kind of insights we can gain from there. We have today here two professors, both very interdisciplinary, one coming from computational linguistics and working her way towards machine learning, and seeing what kind of AI technologies aspects can be used there. And on the other hand, a hydrologist who explores AI to see how we can predict flooding better. They're both not only exceptional from their research, but also according to their output, their impact in the real world, because the topics in which they are engaged in, they touch us as a society in many, many ways. Yufang is looking at natural language processing and especially on fact-checking, the effects on democracy and aspects in this direction. And Daniel Klotz is looking at disaster management, specifically in the flooding arena. And they will both show you not only on the one side their scientific insights, but on the other hand also what does these kind of applications and really mean for us as a society and how we can really change the world with them. And with this, I would like to start to introduce Yufang Hou. She is working at the interface of linguistics and machine learning. She gained her PhD in computational linguistics from the University in Heidelberg, and also did a very short postdoc there on discourse understanding. And then relatively fast went on to work with IBM. And there in IBM, she was working in the project Debater. I'm sure you've heard of the Debater. It's a really cool project. If you listen to this AI debating certain topics, which you can basically feed it, you really see the power which NLP together with AI can really produce. At the same time, or in parallel, when she was at IBM in Ireland, she also worked closely with Professor Irina Gurevich. She is at TU Darmstadt, and she's one of the top NLP researchers. And so there, Yufang did not only do a lot of great research, but also teaching and getting in touch with the students, and also getting excited about teaching. She's now our full founding professor on natural language processing. And yeah, and now she's working on basically summarizing scientific papers, outputs in a way that this can be used for fact-checking. And if we are now looking into the world and see that all this propaganda is aiming at confusing us in a way that we don't know anymore which facts can we actually trust and what's fake, what's not fake. After a while, it gets really confusing. And this is where Yufang can help. Please, the floor is all yours.
Thank you, Stephanie. Thank you, everyone, for joining us today, in person or online. So today's topic is empowering science with AI. For the next 30 minutes, first, I will reflect on natural language processing, NLP, from the perspective of research on language models. Then I will talk about a few topics I've been working on. Finally, I will discuss some open research questions. So let's dive in. First, to make sure we are on the same page, I'd like to give you a 1-minute short introduction about what a language model is. A language model is a probability distributions over word sequences. It computes the probability of the next word given the previous context. For instance, given the previous context, a boy is eaten an. So the most likely word is egg compared to email. This example may sound trivial for you, but it took researchers many years to develop models and algorithms to approximate the probability distribution of the language units. So to prepare for this lecture, I went to the ACL anthology to check how NLP researchers say about language models. So the ACL anthology is curated by ACL, Association for Computational Linguistics. It's a great resource for NLP researchers and students because it provides open access for all NLP-related conference and workshop proceedings, as well as journal articles. So I went to check the conference proceeding ACL 1979, which is the first conference, first ACL conference at ACL Anthology. So at that time, there are in total 24 papers organized into 4 sessions. We have language structure and parsing, we have knowledge organization and application, and we have dialogue, we have applications. None of these papers is about language models. However, while browsing through these papers, I noticed at that time, every session chair wrote a very short 1-page comments to summarize the papers in the corresponding session, as well as reflect on the field. I looked at some of these comments. I personally found them very inspiring and still relevant today. I will come back to them in a few minutes. So apparently, it's not possible for me to manually look through every conference proceeding. So I used deep search to plot the number of papers from the ACL anthology with language model in titles from 1979 to 2024. This is what I got from deep search. The trend looks reasonable, but the numbers on the y-axis doesn't look right for me. So I tried another one on Scholar GPT, which is an app built on top of OpenAI APIs that it can interact with the outside resources when necessary. This time I got another plot. Well, now I have 2 results for the same task. One is from DeepSeek, another is from Scholar GPT. Which one I should trust? And what is the gold standard here? Eventually, I manually downloaded ACL BB file from the ACL anthology and wrote a script myself to get this plot. So I did manually check a few conference proceedings to make sure that my script extracts the correct number. So here you have to trust me that I did provide the gold standard for this task. So now let's take a closer look at these paper titles from different time period. First, during the statistical NLP period, around from 1990s to 2010s, the word cloud shows that the research about language models is strongly associated with machine translation and speech recognition. Now, in the next time period, from 2010 to 2017, which I call the neural NLP period, the first neural NLP period, despite that machine translation is still a prominent topic for language models, we've seen other topics are emerging, such as neural networks, recurrent neural network, representation, and embedding. So here, two papers are worth mentioning. One is word-to-vec paper in 2013. Another is global embedding papers in 2014. Despite these two papers are not reflected in this word cloud, both of them represent classical static word embeddings that helped a lot of NLP tasks. Now let's check what's happening after 2018. So I'd like to quote it as a second period of NLP research. With the release of the BERT model in October 2018 and ChatGPT in November 2022, the research on language models entered into a new era. So the large language models start emerging as a dominant research topic, together with a lot of other subtopics, such as pre-training, fine-tuning, probing, prompting, alignment, as well as hallucination and bias. So for the past 5 years, really a lot has happened in the world of large language models and NLP. I took this figure from a recent survey paper to illustrate this rapid and dense evolution about the research on language models and also the corresponding model artifacts. Consequently, when we deploy these models in the real-world applications, they are changing and transforming our world and our society. However, I still argue that a lot of issues raised in the early days remain unsolved. Let's go back to look at the comments from the session chairs at ACL 1979. The first one is written by Arvind Joshi for the knowledge organization session. And he pointed out that representation has to be adequately support the desired inference. And he also pointed out knowledge has to be updated. And also knowledge representation and acquisition have to be viewed together. So nowadays, the most popular solution with regard to the issue of the knowledge update in large language model is RAG, retrieval augmented generation. So the idea is provided the model with the most up-to-date information when it solves the task. However, in one of our recent papers, we found these models are struggling to deal with conflicts in the retrieved context, especially when these conflicts are implicit and require reasoning. Another comment from the session chair application, David Hess, who is actually created the term of computational linguistics. And he raised the issue, is a computer worth of trust? He wrote, I have asked this question of students, grading the context from simple arithmetic trust. They trust their pocket calculators to give accurate sums and products, to complex personal trust. They would not accept that computer as a friend. So we have, I think, no experience with computers that are functionally worthy of trust in any but simple matters. So in the end, he pointed out trust arises from knowledge of origin as well as from knowledge of functional capacity. So here I'd like to ask a few similar questions to our audience. How many of you frequently use large language models such as ChatGPT, Gemini, Klotz, or DeepSeek? Wow, a lot of hands raised. And next, how many of you believe that these models are trustworthy beyond handling simple tasks, such as calculation? Okay, some hands raised. Okay. So next question, how many of you would trust these models for important matters, such as trying a medicine for a condition? No hands. Good. So in general, we still need to do a lot more to make sure these models can be safely deployed for the real-world applications to avoid incidents like Air Canada chatbot accident. So to summarize this part, I think nowadays we are living in a very exciting era of NLP and AI. It's filled with, from one side, a lot of remarkable innovations, and on another side, complex challenges. So with this, I will dive into a few topics I've been working on. First is document-level NLP. Despite a lot of certain models achieve a lot of remarkable advancement, recent study point out these models are still struggling to deal with non-context reasoning. So in one of our work, which is referential discourse modeling, here the goal is to come up with a model to understand how a reader would understand every entities in a discourse and figure out relations among them. For instance, in this example, in the first sentence, the text introduces a new entity, the earthquake, into the discourse. So in the second sentence, when the reader reads a resident, it's more likely this reader will infer the resident will link back to the marina, a city mentioned in the first sentence. So here its information status is not new, it becomes mediated through the reasoning. And then finally, the she in the second sentence, it's a typical co-referent anaphor. It refers back to the same entity, a resident, that was introduced before. So the information status for she at this time becomes old. And for referential discourse modeling, we are particularly interested in a task called bridging inference or bridging resolution. The goal is to read the document and identify the bridging anaphors such as residence, limited access in sentence 25, and link them back to their corresponding antecedents, which is buildings with substantial damage in sentence 24. So over the years, we developed a series of models to extract first entities from the whole document and infer their information status and extract such bridging pairs from the whole document. So far I've talked about document level understanding within a single document level. What about cross-document understanding? So next, I will using one example, project debater within the context of argument mining to illustrate our work in the cross-document processing. Project debater is an IBM research grant challenge after Deep Blue and Watson Jeopardy. The goal is to develop a system that can help humans to obtain unbiased information by processing pro and con arguments on both sides for the complex issues. In 2019, Project Debater had its debut in San Francisco in front of the live audience. So it debated with human debate champion Ms. Harris on two motions in the Oxford style debate. So it's running like this. First, we have moderators to introduce a motion such as we should subsidize preschool. Then projector debater is here. And then the Ms. Harris, each side will give 4 minutes opening speech, followed by another 4 minutes rebuttal speech. And finally, each side will deliver a 2 minutes closing statement. After this, the live audience will vote on different dimensions, such as which side is more convincing or which side gives us more high quality evidence. In 2021, we wrapped up the whole project and published an article in Nature. So the figures on this slide illustrate the overall architecture of Project Debater, and many worked on the argument mining component. So now if I did some retrospective thinking, so one piece is missing in project debater, which is fact-checking. So back then, given a motion such as we should subsidize preschool, we extract a lot of high-quality claims and then corresponding supporting evidence from across 400 million news articles. However, we didn't check the veracity of these claims. So in the next topic, NLP for science, I will try to combine these two things together. I will talk about our recent work on applying argument mining and fact-checking for scientific misinformation reasoning. So first, let's look at a real example. In July 2020, Dr. Steiner Emanuel's speech at a conference went viral on internet. There she claimed that hydroxychloroquine is a cure for COVID-19. This claim got widespread on internet and had a huge impact on the population. I just highlight a few here. One goes, Dr. Emanuel was on fire, everyone should listen to her. Another goes, Dr. Steiner Emanuel, my new hero. They are warriors for the truth. This doctor needs to meet with Trump. The reason, one reason that her speech is so convincing is that she cited a scientific paper to support her claim. She said, the study that made me start using hydroxychloroquine was a study that they did under the NIH in 2005 that says it worked. So this is the first page of this paper she cited. If we look more closer to the paper, somewhere in the context, it says, a post-infection chloroquine treatment reduces SARS-CoV infection and spread. It seems it can be used to support her claim, right? But if we look more closer, this study is an in vitro study, meaning all experiments were carried outside of a living organism. Second, this study targeted SARS-CoV-1, which is a different virus, SARS-CoV-2, that causes COVID-19. So if we put all of this evidence together, it's not possible to infer that a drug will work as a COVID-19 cure in a living person from an in vitro cell culture study on a totally different virus. So now the research question is, given a false claim that cites a scientific paper to support it, instead of simply predict the veracity of this claim, how can we develop a model that tells us why this is misinformation and how this misrepresents the scientific paper? So to solve this problem, first, we develop a theoretic argumentation model. So given the false claim, given the paper, and we want to reconstruct the financial arguments such that it can be used to support this false claim. So first, we need from this paper, we need to extract somehow these premises that this false claim is likely to build upon, right? Chloroquine reduced infection of the coronavirus. And next, we need to identify the relevant context from this paper that are necessary to construct these financial arguments, such as the study used cell cultures for their experiments, and the study was conducted on SARS-CoV-1. So with this as an input, the task is to generate or reconstruct the financial reasoning to support this false claim. For instance, if we follow the context when the study used cell cultures for their experiments, the corresponding financial premise is the results can be transferred to humans because the human body consists of cell structure. So this is a fallacy of composition. So now we have this theoretic argumentation framework. The next task is how can we build a data set? To do so, we create two data sets based on the fact-checking articles written by the domain experts from health feedback. So first, we manually identify the fact-checking articles that contain a false claim and also make sure this false claim cites a scientific publication to support it. And then we manually carefully read these fact-checking papers. Our annotators annotate this financial argumentation graph. And finally, we have two math students from the biology. They read the corresponding papers and get the passages linked to the paraphrase version of this financial context. So overall, this is how our annotated dataset looks like. With this annotated dataset, we carried out a series of experiments. First, we say, how about current large language models? Can they reconstruct these financial arguments? The simple answer is no. For all the models we tested, they perform quite poorly on this task, especially when we provided them with the passages from the paper as evidence. Next, we say, okay, what about the existing sort of fact-checking models? Can they directly tell us this claim is false? Surprisingly, we found the automatic fact-checking models predict most of these annotated passages support this false claim, despite we trained these models on the scientific fact-checking dataset. And next, we check, how about large language models? Do they know the veracity of these claims? The answer is yes and no. So it seems that models such as GPT-4, if we only provide this claim itself, it knows this claim is a false claim. So this is not surprising because the corresponding fact-checking articles are likely to be presented in the pre-training dataset for these models. But however, when we say, okay, now I have this claim, and I also have some evidence from the corresponding papers, these passages, and tell me whether this claim is true or not. And suddenly, GPT-4 model say, flip the side, consider a quarter of these claims are correct. So this is not what we wanted. One of the limitations of this study is that we always assume the cited paper is trustworthy, which again is not the case, right? We all know scientific literature is a very complex and heterogeneous space. Every paper has its limitations. Over time, we will have outdated knowledge. And oftentimes, we've seen the contradictory claims across different papers. This is one of my favorite examples. In Inaugural 2019, there's a paper titled, "Attention is not explanation." A couple of months later, another paper came out at EMLP 2019 with the title, "Attention is not explanation," which disagrees with the previous paper. So such contradictory scientific findings can be life-threatening when they influence our decision about whether we should recommend a therapy or a drug for a patient. To tackle these challenges, we've been working on meta-analysis for scientific literature. In the NLP machine learning domain, we propose a new task called scientific leaderboard construction. The goal is to reconstruct the leaderboards directly from the papers. So the leaderboards such as the MMU, multitask language understanding, which is right now is a popular benchmark to evaluate large language models. It contains the papers that reported their results for their methods on the exactly same testing dataset using the exactly same evaluation metric. Our goal is to automatically construct these leaderboards. So a lot of previous work, including our first paper, had an unrealistic assumption. It assumes that these leaderboards are known beforehand, which again is not true because every day we have new papers coming out, right? Propose new task, dataset, or evaluation metric. So in our recent paper, we propose a framework to overcome this limitation, which allow the system to construct a new leaderboard from scratch when necessary. Another work we did about meta-analysis for in the NLP domain is to analyze how research concepts influence with each other. To do so, we first developed a tagger to extract task, dataset, metric, and method entities from the whole paper. And we run a causal analysis framework to analyze for each task what are the most influential research entities in different time periods. For instance, for machine translation between 2003 and 2017, the second most impactful research entity is blue, which is a very popular evaluation metric for machine translation and nature for natural language generation in general. So at the moment, we are working on meta-analysis for biomedical literature. The goal is to reconstruct this forest plot and then the corresponding conclusions, whether we should recommend this drug or this therapy for a patient for a given condition. And then we need to go through this literature, right? Extract evidence from different paper and finally come to a reliable conclusion. So it's not a trivial task because normally it takes domain experts 1 to 2 years to conduct only one systematic review. And of course, we can't have the experts to do such meta-analysis for all possible questions which actually are needed in the reality. So therefore, our goal is to automatically construct such forest plot. It's very challenging actually to extract these numbers from corresponding individual studies, as most of them actually you can't directly extract these numbers from tables. From the tables. I myself, a couple of months ago, did analysis annotation for a forest plot, which consists only 4 studies. It took me really half a day to read these 4 papers and understand how these numbers can be extracted from the original study. So right now we are working on a reasoning-based system to extract these numbers. So, all right. Now I will quickly summarize the talk. First, I'd like to emphasize that interdisciplinary collaboration drives scientific progress. So NLP itself is a very multidisciplinary research field. And I think large language models represents a very successful example of interdisciplinary research. And moving forward, I believe that large language models and AI technologies have the potential to transform scientific research. So in one of our recent studies, we analyzed the impact and influence of large language models in different scientific disciplines beyond just computer science. For instance, in environment science, researchers using these models for land cover classification. So in the next talk, you will hear more insight from Daniel about how to apply machine learning in earth science. So finally, I will quickly talk about some of the open research questions. First, how can we enable large language models to reconcile conflict information when actually the multiple valid perspectives exist? Second, how can we build models that actually can communicate the uncertainty and limitations when synthesizing knowledge? And how can we evaluate a claim for a scientific paper in the global context and integrate this veracity assessment system into fact-checking system to proactively detect and correct this false scientific narrative in real time. So before I conclude the talk, I'd like to thank all my wonderful collaborators and great students I've been working over the years. Thank you.
Thank you, Yufang. We will have like the overall panel and questions later, but maybe are there some questions which go directly for understanding? If there's some, we can already take them now. So I learned that in the future, I won't have to read any of those scientific papers anymore. You can already kind of synthesize this all together. This is very nice. Okay, if there are no questions, then I would hand over to Daniel and first introduce, of course, Daniel to everybody. Yeah, Daniel Klotz doesn't come from that far away. He studied at the BOKU Vienna, and he did his PhD in hydrology. So basically, he looked into models of hydrology and see how that can be fitted to specific regionalities and then be improved. He then decided to do a postdoc here at JKU together with Sepp Hochreiter to dive deep into machine learning and in order to see what machine learning can actually do for hydrology. So this is this typical interdisciplinary phenomenon. So if you come to a certain point in your discipline, then you want to see what machine learning there can do for you. He then went on to the Helmholtz Center for Environmental Research and worked there in a group on compound environmental risks. So this group was headed by Professor Jacob Zeichler, which is a very well-known person in hydrologies. And so the point was to now really to synthesize all this. So today, he is a visiting researcher at Google, as well as a assistant founding professor at ITU. And when I asked him how to characterize his research, he said, well, basically, it's only a very simple question he's working on. When is how much water where? Sounds very simple. Sounds like you could be easily answering this, but he will show you now this is quite more complex.
Such nice words for a measly assistant professor. Yeah, it's great to be here. The way I structured my presentation is I have two parts, one at the start and one at the end, which are a bit giving you a different flavor, and they're inspired by my work as a postdoc and working with PhDs. And then the main part, the main body of the work is about hydrology. I don't know how much of you knew what hydrology is in the first place, but after this talk, you will know. Kind of. So as a first example, to wet your flavor, to get you ready, think about machine learning. And each PhD, each student, if you do machine learning, at some point, you have to build a classifier for dogs and cats. It's mandatory. And usually, what you do is you have what we call here in-distribution data. You plug this into a network, and you have a lot of labels, and then they tell the network if you're wrong or right, and then the network learns to classify dogs and cats. And I choose this example here, this work here, because I think Yufang works a lot on how we can deploy models in the real world. And this is also work which goes into this direction. So I cannot explain too much in the technical details. I don't have the time for that. But the idea here is that we can always get a lot of other pictures. These are the aux data, so auxiliary data. And then we can basically enrich the network with this data, for example, chickens and dinosaurs, because you asked. And then the model can learn to differentiate between what's outside there, what can be done, and what's actually the task that it should solve. And the trick here is, because this data is so huge, each day we produce millions of images, and we kind of have a very nicely motivated function which tells us which are the important ones for the model to learn on. You can read more about it here. But to show you a bit how this would look like in a real example, not just with like comics, and also maybe to show how it could look like. So what you see here, what happened here is we trained a model on a data set with 10 classes, and then we pushed in a lot of data. We pushed in all the data for the training, we pushed in auxiliary data, and we pushed in outlier data, arbitrary other images. And then we cut away the last layer, and it's a huge 500-dimensional vector which comes out of that. And so we projected it down to 2 dimensions, and that's basically what you see here. And you see that there are the 10 classes in there, but you have to be really careful to even see the orange dots here, because the model has not learned that the data which has not seen before, to put it somewhere else in the space. So it always tries to classify everything as a house, as a cat, or a dog. And now, of course, I wouldn't show you that if our thing does not work. Here you see the same thing, but after we trained it with our method. And now you can see it has learned to put all the auxiliary data away, which makes sense because this is what it's trained on. And most of the outliers we could also remove. Not all of them. So it can also be that some of what we think is an outlier is actually this class. It's often difficult to say. But you see that the method actually works very, very nice. One thing I would like to say, I motivated this with cats and dogs because that's fun. But this kind of problem occurs very often if you deploy models in the real world. You can also think about, I don't know, bank transaction. You want to enable them very easily, but then there are this very strange one, which, I don't know, you go home tonight and then there's one from South America, and then we should detect that. And this method's kind of going to this direction, it is kind of this flavor of research. Okay, now to something completely different. Think I want to motivate my main body of work that I show you with an example of a canoe. Think that you're a canoe enthusiast and you want to go canoeing tomorrow. So you look at the predictions and maybe you look at the weather with prediction, or maybe you have a model which tells you how much water or how fast the water in the river that you like to canoe on is flowing. And if you think about that, then this gives us a very interesting risk proposition. So here on the x-axis would be like the amount of water or the speed of water. And if it's very slow, it will be very boring for you, so you will not go out. But if it's very fast, it will get more and more fun until we reach a certain point. And this, almost everyone will reach them when the water is too much, too fast, and then it gets really dangerous. And you might even have a risk of dying. And these risk curves, they will, of course, look different for everyone. Some people are more risk averse, some people are more risk takers. But from a modeling perspective, this is extremely interesting, because if you're wrong here, it will always not matter, because if our model makes errors here, no one cares because you will not go out with your canoe anyway. But if you make errors here, then it can become life-threatening. And as Stephanie already said, figuring out when there is water where is like the big question that I devoted a lot of my life to. And I had this introduction for hydrology, and it's the science of the distribution and the movement of water on Earth. And basically, you can think a bit, all of it is basically motivated that we as humans try to manage the natural variability of the water. If there is too much, it's not so good. If there is not enough, it's also very bad. And yeah, all of this, if I was going to say it, it sounds so easy, but in practice, it's actually a very deep and complicated problem. To give you a bit of a feeling how big this problem is, this is data from EMDAT. It's a huge database which collects all large natural disasters that occur in the world. And I hope you can see the dominating ones in terms of frequency. So the y-axis here, you see the frequency of occurrence, and then the x-axis the year when they occurred. And both drought and floods are hydrological disasters. And a lot of extreme weather, I should say, is also often connected to hydrological disasters. And here you see the same data, just plotted differently, but I hope you see that these are quite dominating in terms of frequency. And as a machine learner, you also think, I should be able to exploit this. This also means there is a lot of data. If I can just connect the different rivers, maybe I can learn something from it. And that's kind of the motivation for a lot of my work. So I will just grab something to drink. It's not the most exciting slide to stop, but my I also don't manage. No, it's not. Have it. Okay. So now I have to tell you a bit, teach you a bit about the history of hydrological modeling. So in classical modeling, there are multiple philosophies, but two that I want to mention to you. One is you have a model of a river, and then you calibrate it, so you adjust the parameters of the river for each basin individually. We call this basin-wise or basin-specific. So each model, even if they're physical, there are parameters which you have to estimate, and you can always adjust them and find a better optimum. And then we have a second modeling philosophy, which says, well, we are scientists, And fundamentally, there should be one function which explains all the different rivers. And there we've tried to find one common set of parameters for all different rivers. And basin is a technical term, but you can think of it as a reach of a river at some point. And the models usually take in something like temperature and precipitation, and then they estimate how much water there would be in the river now. And so maybe a bit on how to evaluate them. So what we see here is a cumulative density. And what you have to think is this line is constructed of a lot of points, and each of those points is one river that we evaluated over multiple years, and then we computed an NSE value. And the NSE, for those who are mathematically versed, for historical reasons, when we in hydrology compare the stream flow with a simulation of the observation, and we compute the R squared, we call it NSE. And for those who are not mathematically versed, what you should think is one is the best possible point you can reach. That's the best model. It would explain everything, even the measurement noise. And it goes into minus infinity, but no one cares for models which are not good enough. And so how to read this? So basically, you cut in here at 0.4, for example, and this would then tell you that 40% of the basins have an NSE below 0.5 or something like that. Okay, I will use this a lot. So there's a question. Sutcliffe efficiency, but don't worry about that. Just remember, good here. If you would have a perfect model, it would be a straight line, and the more you are coming here, the worse. It's just one metric. There are thousands of them, and people discuss ad infinitum which one to use, but this is the one which is by far the most one used in hydrology. So this is how the picture normally looks like. Here we have two models. One is the WIC model, which is the old national model used in the USA, very common and widely used. One is the MHM, which is developed at the Helmholtz Center where I worked, and I did my PhD with that. It's one of the best models in hydrology from the classical models. And what you see here is that if you have a basin-wise approach, you're always better than if you have a regional approach. And people discuss this very often. Why this happens, and the explanation that I like the most is these models have a limited capacity, and if you then optimize them for each individual basin, you have more degrees of freedom, and so you also get better. But if you have a regional model and you do some kind of optimization, the model has to kind of find the best solution for all of the basins, and so it gets worse. So, but this kind of restriction, you don't necessarily have them with machine learning. And so this is when we came in. And for us, it looks exactly the opposite. So if you have a basin-wise approach, we are bad. And then if you have a regional approach, we got better. So this was very strange back then. And maybe I should tell you a bit on how our approach works. Basically, we have two kind of inputs for our model. One is, I guess I told you, precipitation, radiation, and temperature, and stuff like this, all kinds of meteorological inputs. In reality, there are much more. But then we also have physical properties or other properties which describe the basin. And you can think about this as a conditionalization. So now we train one model for all the different rivers, but we tell the model actually what kind of property the river has. It is conditioned on the kind of river, and it gives us different prediction. And we use LSTMs for that, as I mentioned from here, and one reason why I started going into machine learning. It's also not arbitrary, the choice. The LSTMs have a structure which really fits well to the problem. And over time, we expanded it also a bit. But for now, I think this is fine. And if you want to see the difference, what happens? One common problem if you go with LSTMs for a single basin approach is that if in the past you have not seen some large events, which are in some sense the most important ones, it will never be able to reach those high events. But if you have a regional approach, it learns from different rivers, and then you almost always capture some very high events. And you can see, this is an extreme example, not all of them are this extreme. But here you can see it gets much more dynamic and much better, the model. So it can, even if the Sutcliffe maybe doesn't look so much, it can have very important difference in terms of quality that you get from your observation. And in another study, we could also show that if you want to have uncertainty estimates, so if you want a model that it tells you how Sure it is. Then it's also extremely useful to not just look in the past, but look at different rivers and learn from them and events that happened, which are similar to the ones that we use. So I don't have the time to go much into that, but let's go back to these regional and single basin models. So here you see an evaluation of the regional ones. And here we have a lot of different single basin models. And now it's just like, I'm super proud. We outperformed all of them with a machine learning approach. And this kind of steered a very big change, I think, in the community, where now the LSTM is by far one of the most established models, I think, in the most established machine learning models, but in general also a very well-established model. We also competed or participated in a model intercomparison project, which was led by Juliana May, an amazing researcher who is now in Canada. And well, to make the long story short, but this is a different criterion, but it has the same, it's called KG. And it has the same property, one is the best, that no one cares when they get too worse. And what you see here in this part of the presentation, here all are different, each column is a different river. And for each river, we traded in the past, and then we evaluated in the future. And you can see that the LSTM is the best. But maybe even more interesting is this column here. Here it's not only in the past and the future, but we also transposed it to new rivers, which it has never seen before. And here you can see that the gap is even bigger between our models and the other models. You can also see what I told you before, this classical differentiation, that the single basin models tend to be better than the regional models. Ours is a regional too, but it's much better than both single and the classical models. So this is super cool, I think. And I benefited a bit from it, so maybe I'm biased. What can you do with this now? So one example is here, also work from Helmholtz. We trained the model on all of these blue dots where you see here are rivers, and we trained the model from there. And then we used it for all of the blues and gray dots to generate a new data set for Europe, basically. And then you can use this data set to do science. And to show that that works, we reproduced a study from Günter Blöschel, who's also a famous hydrologist in Vienna. And I show you a bit how we do that. So what you see here, well, I hope you can see it. It's a bit mushy because it's also dense. Small little arrows who dance around, and each year they go somewhere else. And basically the color and the direction tells you when in the year the biggest event happened. So at some point, you see then sometimes that some specific events really change the whole map. And this is often huge events which happened in Europe. And you can see how they spatially basically behave. And if you aggregate this to some circular statistic and aggregate it over time, over the whole time that we have available for each year, you get a pattern like this. And for example, you can see the influence of the snow here in the Pyrenees, in the Alps, in Northern Europe. And then you can see also this shift from west to east and from north to south, and the general behavior of the hydrology in Europe. And I don't know, it's not really super good visible, but you can see the Rhine or the Danube also, how strongly they're influenced from the Alpine, so basically from Austria. And maybe for me, the most exciting project that came out of it is with Google. So it's a bit commercial, I'm sorry. They took this and expanded it. So under the hood, there's a lot more going on. And we have now a model which works on the whole world, 80 countries. We reach 400 million people. We give out warnings and predictions all the time. I encourage you to visit it. I think it's super great. I believe that this happens very seldom in a researcher's life, and I had this opportunity to go there. It was like a rocket. For me, like flying with a rocket was amazing. It's also very well documented and open, and it's an amazing project. And already now we go for the next phase for next year. And I hope you can, maybe not as big as launch as this year, but also continue to work on this. And that's it with my work. So I do have prepared a dessert, since you're in Austria, for your mind. It's another thing that was inspired by a very smart student from JKU. And here this a riddle, and I found then in the preparation of this lecture a simpler kind of way of this riddle. And yeah, it has nothing to do with my work, but I found it fits in very well. So you have to wait a bit for the food and the drinks. Oh, this is unfortunate. What you should see here is that one of my topics are obviously risk. But another topic, which maybe is not so obvious, or another motive that often appears in my work, are multitudes. So we use auxiliary data and on top of the normal data to train. We use not just one river, but multiple rivers. And then we try to improve the models with that. And here is a very nice example of what kind of the thinking that can come up with that. And it's an equation. So I was told I always need to show an equation. So here it is. So imagine you're playing a game and it goes over time, like hundreds of time steps. And you start with some money. And then you throw a coin. The coin comes either head or tails. If it comes head, you get whatever money you had, you get the half of it on top of it. But if you lose, 40% of what you had gets thrown away from it. And if you do a classical, so this is the expectation, and this is for a given time step, then it will look like this. So the difference is 0.1, the half of it, and you can make a power on to the power, so you know. Maybe some people already see it. So if you just play for long enough, your expectation exponentially grows, and you will always win. So I plotted this. So in theory, if you would work like 500 time step and play, then your expectation is extremely high. This is a log transformation, same data, I just applied the logarithm to it. And here you can see, oh, it's exponential because it's linear in the logarithm. Don't worry, there is a point to this. But now, if you simulate the actual play, it looks like this. So all of those are, I think, 200, maybe 400 runs where I had to play it. And you can see that all of them lose. So what's happening here? It's a good slide to drink. OK, so what's happening here is that in the expectation, there are some, they're very unlikely to happen, but some of the players will win a lot, almost everything. And they are even faster than exponential, actually. And so your expectation goes up, albeit almost everyone loses. So that's the kind of game. And maybe also you can see, some of you can see it, the reason why this happens is here we have actually very, very small numbers. And yeah, this is just a linear fit for you to see. And what happens if once you reach 0, your game actually ends because you have no more money. But the expectation can still increase because the mathematics doesn't care about like that you can actually not play anymore because it can have infinite players. And theorists or a lot of scientists like this kind of model. So this was a model because you don't have to like, look at it and with reality, but you can attach it to all kind of things. So in this paper, what they did is basically they said you can see that it can look like a country can become rich and richer. I bet most people get poorer and poorer just because you have very few we can become so rich that it goes up. But I think you can also apply it different. Imagine that you are part of a young university which was just founded, and then you have a lot of professors. And it might be worth to go to risky propositions, which might fail, just to get very good ones, which then change everything. And that's really the finish now.
It was a fun end. Could you have predicted the St. Pölten disaster with the Google?
No, that specific thing not, but the overall event, we actually predicted it quite well. But I have to say all models predicted it quite well. So this was not where we could say we were much better than other models. So this was actually overall, I have to say, from what I evaluated, all of the models were pretty good at predicting it. And
we didn't listen.
Well, some specific parts, very small parts, like the thing that happened in St. Pölten, was just didn't shine in the models. And there is always some kind of precision and how good you are, and things happen with such big events that I think can become unavoidable. And I don't know if you remember, some weeks later, there was a big event in Spain. And this we predicted very badly, for example. So it's not all solved yet. So especially these dry areas, which are kind of important or somewhere, and flash floods, there's some very big kind of research that's still ongoing. So others like this in St. Pölten, I think these are fine with how we are, but other events not so.
Okay, there's still a lot to do.
Yeah. And can I just say
Yes.
another nice thing? We sent out a lot of warnings for that event, actually, also in Czech Republic, because very often when we had before that, when we sent out warnings, it was in countries where people didn't use the internet so much. But here, this was one of the first times where we really could see how people take it up. And then it was very nice also to send out so many messages and see how the behavior changes. Yeah.
Yeah. So I think this is one characteristic of ITU professors, that they are so excited about what they're doing and actually making a real world impact. So just to get a little bit warmed up for the questions round, and then later on I will ask you to also please ask your questions, so we are here all about interdisciplinarity. So clearly, you two are very interdisciplinary researchers. So, but how did it come to that point? Why did you want to endeavor into different technologies to solve your problems?
Yeah, for me as an NLP researcher, in the beginning, I focused more on building computational models to understand language from the semantics perspective. But later, the more I worked on NLP, the more I realized really human language is deeply connected to a lot of fields beyond just computer science and linguistics, because language reflects our human cognition, and language also reflects our culture. Language also reflects our social norms, social dynamics. So really to understand language, and we need to combine the insights from these different disciplines, such as we need insights from linguistics to understand the syntactics or semantics, and we need insights from cognitive science to understand how humans process language. We also need insights from social science to understand how language is shaping and being shaped by our social dynamics. So from the applications perspective, I think it's more interdisciplinary. For instance, when we build, say, applications for medicine, for education, for in legal domain, we really need this domain knowledge to help us to build more effective solutions. I think in general, really, it's the blend of this technology and then the human-centered view that makes this interdisciplinary research in NLP both very challenging and also incredible rewarding for my journey.
Daniel, your take on it.
Yeah, for me, it was during my PhD. I worked on regionalization. So this kind of problem, how can we make a model which has the parameters shared among very different rivers? And back then, it wasn't clear at all that this model would be so good. And so we started by trying out making models and then making a model of the model with a machine learning model and then emulating that model and playing around. And at some point, while we were doing that and trying to find out, is this something that machine learning could tackle? It became clear that this is like a shoe perfectly made for my feet. And I went in and fell in love with machine learning. And for then, I applied it everywhere I could. Followed all the news and yeah, I came here, make the postdoc here, and never stopped, basically. So for me, first came the problem, and then I abstracted it, and it came a more general view of machine learning. And then from machine learning, I came back to the problem again. And this is kind of how the circle goes, I think, for me. Yeah.
Yeah, I think it's always a very personal story with which interdisciplinary research starts. And this is really what we want to bring in or to motivate in our students. Yeah. So do you have an idea on how we can foster this interdisciplinary curiosity?
Yeah, I think it's very easy. Who is not excited about machine learning these days? It's like trivial. No, I'm joking. So I think some spark needs to be there. Else, I'm not sure if you can ignite it. But if it is there, I think it often follows very natural for thinking about projects and then seeing, oh, there is a method which might be very helpful for this project to go for it. And then they learn, oh, but I can also tackle it with this different method. And then I get maybe a different result. And maybe they interact with each other. And then I learn something from it. And then you grow it up from there. And at some point, if it's like me, it becomes just obvious. And yeah, it's a spiral. Yeah.
Yeah, so you have some additional ideas?
I think the spirit of ITU would be a good starting point for this to create to inspire more curiosity from students. I think first we need to have this seed project that is designed in a way that it disciplinary in nature. And then that really requires students from the different backgrounds to come with ideas, to brainstorm, to find a solution. I think this is important. Another aspect I want to emphasize is here, I think during this process, we also need to teach students to tolerate the failure. I think this is very...
You have to tolerate the failure to get that.
Yes. Yeah, this is point I want to emphasize.
Yeah, so an error, not an error aversive culture, but the opposite, right? So to trial and error and so forth. Yeah, with this, I would like to open the floor for questions. Are there any online? Are there any from you? Philip.
An obvious question, but I mean, you both work with sequential data somehow. Wouldn't it be worthwhile to throw these transformer models on your hydrology data?
Oh, maybe we already tried that.
Daniel, this question. Yeah. I think the first time I met with him.
Yeah, it does work, and with effort, you can become as good as LSTMs. So, okay, maybe this is a funny story. When I came here, one of the first things that I wanted to do is like, because everyone in machine learning was doing transformers, so I thought we need to update this and also go to that direction. But it's very difficult to outcompete that, especially if you want to go to different rivers. And it's just the structure of the LSTM fits the actual problem very, very well, while the transformers does not. Now the hypothesis is that if you would have more data and less noisy data, at some point the transformers would take over, but we don't seem to be in that regime yet. So that's a bit the hypothesis that we have.
Yeah. How many percentage of all the rivers in the world have been modeled?
Modeled? Oh, I don't know. So I cannot tell. Modeled probably, not just, if you take all the modeling groups, then I would say it's a lot of them, 99 maybe. Okay. Yeah. It's, but then, you know, there are very small parts of the river and it's like a fractal problem. So it's always the question, what doesn't it mean? If you model the Mississippi, you model half of America basically, but that doesn't mean that you have a model for a small river somewhere in the US. Similar, if you would have a model for the Amazon is just a big sine curve basically. It's so big. And it doesn't mean that you will have a model which predicts some very small river in Brazil. Yeah. Yeah, but we do plan to connect our expertise and we have some ideas. Teaser for the next time, yeah.
A question from online. Why is a local LSTM, after extensive training, not able to get the same performance as a regionally calibrated LSTM?
I tried to show that. So one problem that we have is that if you just look at one streamflow time series, it happened to be that it's actually it is extreme value distributed. So what happens is that in the future, it's very likely that peaks will be higher than the ones we've seen in the past. And the LSTM has these properties, it's called gating. It can never predict something bigger than it has seen in the past. It's just an intrinsic limit of the architecture. And that's a big advantage if you train spatially on multiple, this is a regional model, on multiple rivers, then there's always some river where you have something very large happening, and it kind of learns to transfer this knowledge to the river that you actually predict, and so you get better at that. I think there was a question here.
I'm not an expert on your topic, but generally, fact-checking, you process, I don't know, scientific papers, and you put them all together, you give it different weights, and you do a lot of work with it, and then you sort of can tell us what is trustworthy, what is not. So with your coronavirus, I don't know, some people believe they take some fertilizer or horse medicine, they become coronavirus resistant, but okay, maybe not. But there are some common knowledge. If you shoot yourself in your brain, you're not becoming corona resistant. So there is some sort of facts that are for us obvious, but in the model, I think if it's not all statistical and stochastic, can you take this into consideration? And there are some hard facts that we all know, but maybe the model doesn't.
That's a good comment. Thanks for the question. So that's one of the reasons we developed this model. So previously, if you look at checking the current fact-checking models, so the task is, so of course, this fact-checking in reality is more complex. But when we abstract this problem into a scientific research question, so sometimes we simplify things, right? In the previous fact-checking model, a lot of times is predict the veracity of the claim, whether it's true or not. True, false, or half true, without any explanation. So that's motivated us to propose this argument mining framework into fact-checking to explain me why the model thinks it's wrong. This is my reasoning process. So as a human being, one makes the decision according to your explanation, whether I should take this medicine or not, and then I can follow your explanation path, and then I can make the decision whether to what extent I can trust this. But of course, there's a lot of work to be done in the future. As I pointed in the end, when the model gives this explanation, and we need to communicate what are the model's uncertainty about these explanations. So we need to calibrate this. So I think in the future, there's still a lot of work to be done. We definitely not think this is just like we simply plug in these things and they can do fact checking for every claims. No, not at all. Instead, we propose to have models working with the humans, human fact checker in the beginning, and in the end, perhaps each one of us. I think it's our responsibility in the end also to fact checking nowadays, whether this is true or not. So I think so this is just the beginning, but in the future, we need to develop better explanation models for fact checking.
I think it's also like then we need a hybrid modeling with like, I don't know, physics informed or chemistry informed or whatever models, depending on whatever the topic is. But this common knowledge thing, this is really still the holy grail. There was a question there.
The machine learning model is guessing what's wrong or not.
You mean we were using machine learning to predict whether this fact is true or not.
Faster, to respond faster.
So the model itself, yes, can, if I understand the question correctly, it's the machine learning can fast respond to these false claims, but to what extent we should believe this is indeed, we should correct this false claim. So I think with this regard, we still need to have the humans to be involved. It's humans' responsibility to make the final decision.
In my question, I'm addressing if there's a false shout out, it will multiply within seconds. And how can we deal with that if a human is needed to check?
Yeah, that is good point. That is good. That is a very good point. That's the point we should bring this model early on in the stage. So before it's get this false information get spreaded, and the board just seconds of that, if we can already spot something's going on there, and we can kind of apply intervention there to kind of cut this spread thread of the misinformation.
It's not really directed to that, but it just came to my mind. Turing tests, are very interesting. Now we worked on that for a very long time, and now we have models which come most close to solving the Turing test. But if you ask them, are you an LLM, it will tell you immediately, yes, I'm ChatGPT, that makes the Turing test fail, no? So you kind of have to lie to get through the Turing test. So you have, in some sense, it's not a well-posed test because you have to force the model to lie. And they have another property. If you then tell them, no, you're not an LLM, at some point they will say, yeah, okay, you're right. Of course, because they have this kind of way to please them. I'm probably anthropomorphizing them a bit too much now. But it's kind of, I think, a big thing is still missing, because if you do that to a human, you would have a pushback. You would say, no, I'm not an LLM, I'm a human. So I think there's still something kind of missing in how they behave. Yeah, I don't know, just a thought that I had.
Any more questions from online? Yeah.
Are you working together with insurance companies?
I wish I don't. I think so. Munich Re is famous for having a huge data set like the one that I showed you. But I don't work as of now. But I would love to, actually. Yeah, something that I'm very interested in. Okay.
Yes.
This is a question for Professor Hou. If you're actually working with schools, because having like teenage kids, of course, this fact checking is a big topic, like how to also convey this to the new generation. So do you have some projects also like with local schools, or are you planning to do so?
Yeah, that is a nice idea. I think nowadays we are in this large language model era, and then our kids interact with these models a lot more than we expected. I think another topic I didn't mention today is false information from these large language models. So currently we are working on these false informations from the humans, right? Human kind of is the creator of this misinformation. But what about somebody kind of misuse this model in a way that it can generate very convincing false information, and then get it spreaded over the web, and what should we do? And then since nowadays, these models are trained on this big data set, and then we get this new information from the web and train the models. But what about if one day we train our models on a lot of misinformation? So that is another topic we should be worried about. But as you said, it's absolutely correct. And we should educate our kids about how to interact with the models. So the questions I think during my talk asked, like how many of you would trust these models? I think if we ask the same questions to the kids nowadays, which has a lot of experience interact with ChatGPT, that would be we might get a different answer. So I think it's our responsibility also to develop some, I think, the cool projects, and also develop these kind of tutorials, seminars to educate our kids to be careful and to be mindful when they interact with models.
That's a very good idea. We have schools right here in the vicinity. Also, one of them is project oriented, and so we're actually thinking of having more collaboration. You have to think, I mean, Yufang has been here now for 3 months. Other professors have been here for 4 months. So give us a little time. Yes.
What are we the most excited to do this year here?
To do for this year?
Yeah.
Okay, yeah, the reason we deliver our inaugural lecture together is we had a very cool idea. We want to combine NLP analysis on top of this cool, I think, the models Daniel developed. So we want to, so when sometimes this flooding happening, this disaster happening, right? And then we will see a lot of information flooding on the internet. And how can we extract this information in the text format and combine it with the prediction from Daniel's models and to say what are the causal relations? Some flooding happening, right? It must cause train delay, as we all experienced last year, winter. And people are complaining this and that, but and then after that, what types of information is true, what types of information is false, and then I think a lot of things can be done here in this overlap interdisciplinary project.
Both ways, you can then also use the models to predict what human reactions will be and stuff like that. But yeah, that's a great thing.
Well, I think this is a wonderful way to end this question session, and I would invite you to come to have some drinks with us. And if people are interested, we can still do some lab tours through our Learn Labs. If there is interest, we can offer that as well. Then please go into the far left-hand corner there, and there you will find people to help you.